For the last video for this session, we're going to talk about exponential and logarithmic functions because these functions are easily defined using limits, and you can also derive the properties using limits. If you're already familiar with exponential or logarithmic functions, you can quickly skim through the slides and you're free to skip this video, but if you want a reminder, feel free to listen on. So let's start with the exponential function. And there's actually a whole family of them because they differ in what base they have. So we'll define the exponential with base a is the function f of x that takes a to a certain power x. So keep in mind this is not the function x to the power a. The x here is in the exponent. So for integer values of x, this is easy to calculate. So we have that a to the power 0 is 1, a to the power 1 is a, and if we continue like this, a to the power n, that's a times a times a, n times. So that's easy. We also know that a to a negative power, where n is an integer, that's 1 over a to the power n, and a to the power of a fraction with m and n integer, so here m and n are integers, that's the nth root of a to the power m. So here we take, actually we took a to be positive. If a is negative, you can write down something similar. So this means that we can define the exponential function for integers, here for rational arguments. And so now the question is how to evaluate a to the power x when x is a real number. So for instance, how do we compute 3 to the power pi? And the answer is, well, we're going to use limits. And what we can do is we can take a sequence of rational values, r, rational values that come closer and closer to the exponent that we want to calculate, and then we figure out what the limit is. So for instance, in this example, we can take r3, 3.1, 3.14, 3.114, 1, and so on, and we get closer and closer to pi. And then 3 to the power r is going to be 27, 30.14, 31.49. These are rounded values, not exact values. 31.52, and so on. And if we keep doing that, we get closer and closer to the actual value, which is 31.544, and then a bit. So you see, in the first iteration, we get none of the digit right. In the second, here we have 1 digit, we get 2 digits, 3 digits, and we get closer and closer to the actual value. So here what we end up doing is we compute 3 to the power pi as the limit as r goes to pi with r rational of 3 to the power r. Typically you would not, when you have to compute this, you wouldn't write down this table and then compute all of these values. You would just use your calculator That's perfectly fine. But this argument tells you that, yes, the exponential function is defined even when x is a rational number, is a real number. Quick aside about the graph of exponential function. So there's two kinds to distinguish. So if the base is positive, then the function looks like this. It comes in from 0 and then goes to a point here with 1 and then goes off to infinity. So here we go to infinity and here we go to 0. And if a is negative, then we get the opposite. Then the function starts off, comes from infinity like this, passes through the value 1, and dies out and goes to 0. So we go to 0 in the positive x direction, and we go to infinity in the negative x direction. And then last, well, what do you do for x is equal to 0? Well, then f of x is 0 to the power x. That is 0. So then we just have the flat function 0. It's very good to recognize these graphs on site and to be able to play with them. A couple of laws for the exponential function. I think most of these will be pretty familiar. So one thing that we've already seen, a to the power 0 is always equal to 1. So for a different from 0, a to a negative power is 1 over a to the x. A to the power of a sum is the product, a to the power x times a to the power y. A to the power a difference, that turns into a quotient. And then repeated exponentiation, a to the power x and then again to the power y. That's the same as raising x to a to the power x times y. And then the last, having a product and raising that to a power, is equal to the product of the two terms to that power. So there's a special case of the exponential function that involves Euler's number. So Euler's number is typically denoted by the letter E for Euler, and it's defined as the limit as h goes to 0 of the function 1 plus h raised to the power 1 over h. So this is a difficult limit. If you try to calculate this from first principles, you're not going to get anywhere. This is sort of a value on its own. This value actually turns out to be something around 2.71 and so on. And the definition of the number you can also write a little bit differently as limit as n goes to infinity of 1 plus 1 over n divided to the power n. And so in order to switch between these two formulas, you have to put h equal to 1 over n. And so now, if we take the function f of x equal to e, so Euler's constant to the power x, that is a very special case of an exponential function, and we basically refer to this as the exponential function. So if someone says take the exponential function, they mean e to the power x. You don't have to ask, well, which base do you mean? The base is e. And this is also sometimes denoted as exp of x. And so now there's a small property that we can quickly show, and that is that e to the power x, so that exponential function can be written as a limit as follows: the limit of n going to infinity of 1 plus x over n to the power n. So if you compare to the definition of e itself, we had a 1 here, and now we get an x here. And there's a small proof that we can quickly go over together. So what we can do is we can start by taking basically the limit that we have on the right hand side, 1 plus x over n raised to the power n. And now we're going to set this thing equal to a new variable which we'll call 1 over t. So then this becomes limit of 1 plus 1 over t. And so we have x over n is 1 over t. And in other words, that means that n is t times x. So our exponent here becomes t times x. And so now we use our rules for powers. So first of all, we can write this as 1 plus 1 over t to the power t, and then again to the power x. And now, so that's, if we skip back one slide, that's this rule here, the repeated exponentiation. And now we use our limit laws that says that we can take the power out of the limit, and we get limit n going to infinity 1 plus 1 over t to the power t, and that raised to x. And now if you look at what's in the brackets here, we have the definition of a constant e. So here we get e to the power x. Last, to wrap up, the inverse of the exponential function is the logarithmic function. Again, there's a whole family of logarithmic functions with different bases, but they are basically the inverse of exponential functions. They undo the exponential function. And so how do we define them? Well, we define the logarithm with base a of a value x. We say that that's equal to y if and only if a to the power y is equal to x. So for instance, the logarithm with base 2 of 8, that is equal to 3, because if you take 2 and you raise it to the power 3, you get 8. So this right here, that was my a, my base. This thing right here, that's my y. And the 8 here, that's the x that I'm taking the logarithm of. And we write this, or we say this as logarithm of x to the base a. And so some quick properties. If you take the logarithm base a of a to the power x, you get x back, and this holds for all x. And likewise, if you take a and you raise it to the logarithm of x, you also get x back, and this holds for positive x. There's a couple of properties here to summarize. To calculate with logarithms. So we have, first of all, log a of 1 is always equal to 0. And that follows from the fact that a to the power 0 is equal to 1 for any base that's different from 0. Second property is the log of a product that's the sum of the logarithms. The third extra property is the log of a quotient is the difference of the logarithms. The logarithm of x raised to a power is r times the logarithm of x. And then one important property, so that they're all important, but this one is in particular quite useful. So it's known as the change of base formula. If we have the logarithm base a of x, we can change the base into something else. We can turn this into log b of x, so a different base, but then we have to pay a price. We have to divide by the logarithm of b of the original base. Probably you already know these formulas from secondary school. If you don't, then there's a couple of exercises in this week's exercise session to get this in your fingers, and I would encourage you to have a look at this. And then last, just as there is the exponential function, so we have x of x is e to the power x, so this is the exponential function. The inverse of that is called the natural logarithm. And that is written as ln for log and natural, and is the logarithm base e of x. And this is also the most common logarithmic function that you will encounter. So last, to wrap up just the graphs of these functions, again there are two cases. So if the base is bigger than 1, then our logarithm looks like this. Let me put it in a different color. So it comes in from minus infinity. It goes through the value 1, where it's 0, and then it increases like this, and it continues growing, and it goes to plus infinity. On the other hand, if the base is between 0 and 1, then we have the opposite aspect. Again, we go through 1, but now we come from plus infinity here, and we go like this, and continue on also to infinity. So that was a very quick reminder of those two functions. Again, there are some exercises that I encourage you to have a try at.